everybody. Well, welcome to Friday's mode class. The last time we talked, we were talking about various techniques of figuring out Galois groups, or at least eliminating some possibilities. Here's kind of, I really kind of dig this theorem here. It's pretty specialized, but it's nice. 14.5. Let P be a positive prime. In the integers. And f of x, I want this to be a polynomial of degree p that is irreducible. Over q of degree p. And irreducible. So let's suppose that P has, or that f of x has precisely two non-real complex roots. Suppose f of x has precisely two non-real complex roots. Then the Galois group of f is equal to SP. This is kind of groovy. So for example, suppose f of x is x cubed plus 2x plus 4. Well, I know, and this is the Galois group of f is S3. Because 3 is prime, and f prime of x is x cubed, no it's not, it's 3x squared plus 2, which is greater than or equal to 2, which is greater than 0. So the derivative is positive, which means that actually it's increasing. I guess at -1, this is 1, and at -2, this is probably pretty negative. So anyway, this thing goes something like this. That's got one root, so it's got precisely two complex conjugate non-real roots. So the Galois group has to be SP. So in particular, if you have to have, or if your Galois group is, if your Galois group here is for a cubic, if your Galois group is of order 3, if it's A3, what this theorem says, you have to have 3 real roots, right? Because otherwise, it's not going to work out. And this makes sense, right? I mean, basically, the gist of it is if you don't have 3 real roots, then you've either got one root and a pair of complex conjugates. And that means that there's an automorphism of order 2, namely complex conjugation. That's the machine that makes this work. Prime also turns out to be important as well. So let's see why this is true. Note that since f is irreducible, the Galois group of f is a subgroup of SP. It's a subgroup of cyclic or symmetric group on P elements. But I know a couple of things about it. Number one, the Galois group of f contains some element sigma such that the order of sigma is P. That was from the fundamental theorem of Galois theory, that you have to be a transitive subgroup of S n, and you have to contain an element of order n. Well, so sigma is a p cycle because the only elements of order p in SP are p cycles, right? In fact, I guess you have to get up to S. Let's see, I guess you'd need 2p. Yeah, you don't. In fact, everything in Sn for n less than 2p, any element of order p has to be a p cycle. But in particular, SP, the sigma has to be a p cycle. Also, there exists exactly two non-real complex conjugate roots. So that means that Galois group of F contains a transposition. Without loss of generality, we can say that the Galois group, that the following two elements are in the Galois group. 1, 2. I'll just label these two complex conjugate non-real roots 1 and 2. It's got this transposition that swaps them out. That's the automorphism of complex conjugation work. And it's also got the p cycle 1, 2, 3 up to p. You might say, well, Jim, that's another thing that is important about p here is a p cycle in SP has to involve all of the p numbers that it acts on, right? And you might say, well, Jim, what if it starts 1 and it's some other 1, 7 or whatever? Well, I'm here to tell you that whatever comes after 1, there's going to be a 2 up here somewhere. And take that appropriate power to get 2 next to it. And that's still going to be an element of order p, right? So this is truly without loss of generality. And you can actually prove, and in fact, it's in Hungerford and other places, you may have seen this before, that SP is actually generated by this 2 cycle and this p cycle. In fact, you can replace in that, for that result right there, you can replace p with any positive n. So there's that theorem. So this allows you, so for example, if you've got a 5th degree irreducible polynomial and you notice that it's got exactly 3 real roots by doing calculus or whatever, then game over. It's got to be S5. That's the Galois group. Now, I am going to fulfill a promise, and my promise is, as I told you, that I will give you something that always works. But you will see that this is terrible. But this is a foolproof way of getting your Galois group over Q. So if I give you some polynomial over Q, you can always compute the Galois group this way. This algorithm is, I guess it's probably kind of an old school thing. I got it from this ancient book by Dixon, I guess it is. So here's how this works. So and the goal here is to find Galois. So we will suppose that f of x is irreducible. And since what over Q, that means that we're separate because the characteristic 0, irreducible and of degree. So the first thing I'm going to do is it's got roots. Are the n roots of f in whatever splitting field. So they're contained in the complex numbers, or you can construe them that way. And for each one of these, I'm going to introduce indeterminate. For each of these. So I've got n roots, they're distinct because f is irreducible. I introduce these polynomial variables, if you will, these indeterminates. And I am going to define for every permutation in Sn, any sigma in Sn. So, and there's a lot of these, right? I mean, there's n factorial of them. I'm going to define E sub sigma to be this polynomial in variables, given this way. Z sigma 1 x1 plus Z sigma 2 x2 all the way up to Z sigma n xn, right? So one of the permutations in Sn is the identity permutation. So if sigma is the identity permutation, this particular E sub identity, if you will, would be Z1 x1, Z2 x2, all the way up to Z and xn. But one permutation swaps 1 and 2. So for that one, it would be Z2 x1, Z1 x2, and then Z3 x3, Z4 x4, and so forth, right? You go through all the permutations, right? Yay for us. And you're going to love this. Let g of x now we got this kind of master new polynomial variable, which I'm going to call x. And what I'm going to do is go over sigma in Sn x minus each E sigma. So now I've really, I mean, really what I've got going on here is now I've got n plus 1 variables because I've got x1 up to xn and then I've got x. So this is x minus whatever this polynomial is, and this is taken as a product of everything in Sn. So g of x as a polynomial in the variable x has degree 100 or has degree n factorial, right? Which is pretty freaking big. Now, each coefficient Ci of xi, so let me make this observation. If Ci is the coefficient of xi, oh, and I think I want I'm sorry, x to the I. I don't know. So I do mean like whatever the ith power is. So this is going to be a big mess. It's going to be a degree in factorial in the variable x. So I want to define Ci to be the coefficient of xi. This Ci is actually symmetric in Z1 up to Zn. And so it's a polynomial in x1 up to xn. A polynomial. So each Ci is a polynomial in x1 up to xn with coefficients in Q. So these things actually come together just right so that the z's are put together, and actually the coefficients aren't in the splitting field, they actually are back down in the base field Q. So now you've got this huge polynomial. All the coefficients of the powers of x are polynomials in those other variables, c1 up to, or x1 up to xn. Now, factor this, and this is another task. Factor g of x into irreducible polynomials over, well, let me say in the ring Q, x1, x2, xn, x. Because here, so notice that these are all polynomials in the variable x. All their coefficients come from this ring here. This ring, by the way, is a unique factorization domain because it's a polynomial ring with a field of finite and many variables. This is also a unique factorization domain. So this task, although from a practical point of view is incredibly daunting, it can be done. It exists. You factor this into its irreducible factors. And I'm going to pick one. Namely, what I'm going to do is I'm going to let G0 the irreducible factor of g of x such that e sub I is a root. And remember, e sub I, here I mean by e sub I, the I is the identity permutation. This was just the one that I pointed out was z1 x1 plus z2 x2 plus zn x. So find the factor of which that particular, find the factor the irreducible factor of g of x of which x sub I is. So x sub I is one of these products here, but remember these things are all involve the roots here, and it becomes more jumbled up when you multiply them out and you actually get irreducibles over q. And so this is locked in with some of these other factors. So find the irreducible factor of g of x for which this is a root, and the Galois group of f of f are all permutations of x1 up to xn that fix g naught. So look at whatever this polynomial is, g naught. It's a polynomial in here. And the Galois group is every permutation of the variables x1 up to xn that fix this. And so you've got to plow through all those too. Now, this always works, but it's extremely cumbersome. I challenge you, just for fun, to do this with a quadratic polynomial, right? Here's what's going to happen with a quadratic polynomial. One of two things is going to happen over Q. Number one, that quadratic polynomial will factor into two linear polynomials over the rationals, in which case this process should give you that the Galois group is the identity. The other case is that quadratic polynomial is irreducible over the rational numbers, in which case this process should give you Z2, right? But even there, it's very, very cumbersome. Okay, so before we get to last week's end game, we're going to talk about arithmetic rings. I want to quickly go over finite fields. And the exercise that we did last time, or the homework we did last time, where we kind of took apart the splitting field of x to the p to the n minus x, that's most of what you need to know. I don't want to trivialize finite fields, but I think that we've kind of hit some of the high points. I'm going to approach some of this at the beginning from a slightly different perspective, which hopefully will help out. But then we'll come full circle and see some of the stuff that we've done. First of all, if you have a finite field, so observation, if F is a finite field, then the characteristic of F is equal to P. We've discussed this before because, of course, any field that's characteristic 0 must contain all the rationals, and so can't be finite. So in particular, ZP is contained in F, and F is a ZP vector space. That's one of the cool things about module theory is paying off a little bit for us now, right? Because any subring, so if you have a ring inside another ring, the big ring is a module of the small one. Well, ZP is a field, so F is actually a vector space over ZP. Therefore, F is isomorphic to a direct sum of some number of copies of ZP. As a vector space, this is not, don't think of this as a direct product of rings. It's not what it is. This is as a vector space. We're not thinking about F's field structure at this point, but we're going to capture something important anyway by counting. Now, I did say that F is finite, so this better be finite, right? Because if this is an infinite direct sum, then there's going to be infinitely many things in F, right? So let me make this clear. As a vector space, and so immediately we get that any finite field must have p to the n elements. That's it. Because what do you have here? Basically, anything in here is an n tuple from ZP. You have p choices for every slot, p to the n elements. End of story. So the first takeaway of this is any finite field must have characteristic p. And once you know that characteristic p, once you know that it's characteristic p, then you know that it has p to the n elements for some natural number n. Right, so that's kind of the first takeaway. It's very natural to ask at this juncture, okay, so I know that if I have a finite field, it's characteristic p, it's got p to the n elements, but if I walk up to you on the street and give you a prime p and a natural number n, is there a field of that size? And the answer is yes, and only one, as a matter of fact. And we've seen most of that already in the homework. Let me give you this theorem here that goes beyond finite fields a little bit. Theorem 14.6.2. And this is kind of a nice application of the fundamental theorem of finitely generated abelian groups. Let F be a field and G a finite subgroup of multiplicative group of fields. Of F star under multiplication. Okay, so I've got any field. It can be any field. So throw out the 0 and consider the multiplicative group of the field. Now suppose G is a finite subgroup of that of that group. Then G is cyclic. That's fantastic, right? If you have a finite subgroup of the multiplicative group of any field, it's cyclic. Bang. And there's another consequence to this. So if F is finite of order p to the n, so suppose I have a finite field of order p to the n, then F star, well, F star is a multiplicatively abelian group, and it's finite, so it's cyclic of order p to the n minus 1. So that's something else we can say about finite fields. They're of order p to the n, and there is a single element in F that generates every non-zero element of the field multiplicatively, cyclically, right? So there's some element X that lives in F, and as you look at the powers of X, it cycles through everything in F except for 0, right? That's really kind of nifty. So why is this true? Well, like I said, this is a really kind of interesting application, if you will, of fundamental theorem of finitely abelian groups. So write G as isomorphic to H1 direct sum H2 direct sum HK, where the order of HI equals MI, and M1 divides M2 divides MK. So this is the invariant factor decomposition. Now, let me point out that MK, which is the order of HK, is equal to the exponent of G. Right? So this is the largest invariant factor. This is the largest cyclic piece, right? So this is cyclic of order MK. And actually, since all these other groups, since M1 divides M2, etc., if I take anything in this group to the MK power, it'll be the identity. So for all X in G, X to the MK power is equal to the identity. Right? Every one of them. So every element of G is a root of X to the MK minus 1 is 0. Right? Every element G has to be a root of that equation. But this equation has at most MK solutions over any field. Right? I mean, we know that a polynomial over a field, and remember, this G is a group, but it actually came as a multiplicative subgroup of it is a subgroup of the multiplicative group of a field. This thing can have at most MK solutions. So the order of G everything here is must be less than or equal to mk, which is the order of hk. So the order of G equals the order of hk. So therefore, G is isomorphic to hk is cyclic. Because what we've proved is if you've got more than one invariant factor, there's too many solutions to that equation. Right. So there you go. Alrighty. Corollary. So these are all kind of some nice observations. Corollary 14.6.3. If F is a finite field, then F is a simple extension of ZP. Well, that's also kind of nice, right? Any finite field is a simple extension of Z. Let me do a quick proof of this. F is a finite field, so it contains ZP for some P. And F star is cyclic. Say F star is equal to, generated by, we'll call it Z. Then F is equal to ZP adjoined plus Z. Because just by itself, multiplicatively, this will generate everything in F except for 0, including all the elements of ZP except for 0. Okay. Let me give you another proposition here. Proposition. And this goes toward the Galois group of a finite field. You might wonder what such a thing is. It turns out the Galois group is always cyclic. So proposition T64. Let F a field of characteristic P and R an integer. So here I'm just going to take characteristic P, not necessarily finite, and R greater than 1 an integer. Then the homomorphic, the map given by P sub R given by P sub R of X equals X to the P to the R is a ZP monomorphism of fields. Of fields. And F is finite. It is an automorphism. Okay. So let me just kind of talk a little bit about this here. We've actually pointed out some stuff about this before. Notice in ZP, we have x to the p minus x is equal to 0 for all x in ZP. Some of you might be familiar with Fermat's little theorem that x to the p minus 1 is equivalent to 1 mod p if p doesn't divide x. This takes care of the 0. But if you take anything to the p power and c mod p, you get this. And so in particular, x to the p is x in ZP. And so x to the p to the r equals x inductively in ZP. Right? Because, for example, x to the p is x to the p squared, which is x to the p, which is x, and so forth by induction. So the point behind this is a ZP monomorphism. So whatever, no matter what R is, this actually freezes ZP. ZP is stabilized by this. Of course, we pointed out already that unless the function is the 0 map, then any function, any homomorphism between fields is 1-to-1. So there's your monomorphism. And if f is finite, this is an automorphism. Of course it is, because if this goes from f to f, and if it's 1-to-1, f has the same cardinality as f and is finite, then it's also onto as well. So let me give you this theorem here. Theorem 1465. And I'm going to state it this way. Let P be prime and n in the natural numbers, then there exists a finite field of order p to the n. It exists as the splitting field of x to the p to the n minus x over CP. We've essentially done this. If f of x equals x to the p to the n minus x, then f prime of x is equal to -1. This means, as we've seen when we talked about separability, that f of x is actually a separable polynomial because its GCD with its derivative is 1. That means all its roots are distinct. And an extension of the freshman's dream shows that the roots are actually closed under addition and multiplication. So in particular, the roots create a finite interval domain, which is a field. This splitting, and the splitting field, I'll go a step further, is actually unique up to isomorphism, up to ZP isomorphism. Because this thing creates a field of p to the n elements. And if you have a field of p to the n elements, then it's easy to show that every element satisfies this polynomial. So the splitting fields are unique, but it's easy to see that this one is, because any finite field you have to satisfy this equation. And so there's one and only one field of order p to the n for every prime and every n, and it exists as a splitting field. Now, let me give you an example here. Kind of things we can throw around. So suppose what kind of subfields does this have? Right. So you have to be a little bit careful here, I think, about thinking about division. Notice this, of course, contains F2, the field of two elements. But think of it this way, 64 is 2 to the 6th, and 2 is 2 to the 1. Now, here are the subfields, complete lattice, if you will. Let's see, 8, 4, F2. I mean, you know, there's a field of order 16, and you might say, well, why is the field of 16, why is the field of 16 elements not a subfield of the field of 64 elements? Did 16 divided 64? Yes, but the exponents don't do what you want. 16 is 2 to the 4th. 64 is 2 to the 6th. Now, if the field of 16 elements were a subfield of the field of 64 elements, that means that the field of 64 elements would have to be a vector space over this, which means that 2 to the 6th would have to be a power of 2 to the 4th, which is not true. So the problem is the exponent to divide this one. What are the subfields? Notice they're the dividing exponents. This is 2 to the 6th, this is 2 cubed, and 3 divides this. So this, in fact, is a two-dimensional vector space over this. This is 2 squared, so this is a three-dimensional vector space over this, and it's six-dimensional over this, right? So this is the lattice of subfields of the field of 64 elements, right? Okay, corollary. This was one of my favorites. So I've already kind of talked us through the corollary that there's a field of order p to the n for every n, and it's unique. Here's another corollary, which is really cool. For any n greater than 1 and finite field F, infinite field F, there's this, a polynomial. Of degree n. That is irreducible over F. Okay. Let me kind of go through why this is true. This is kind of a fun one. So let me point out also that the quadratic polynomials over Z2 come as close to possible failing without failing. 3, 4. Right. I guess there are 4 quadratic polynomials over Z2. There they are. This is reducible. This is reducible because this is x plus 1 quantity squared. This is reducible because it's x times x plus 1. This has to be irreducible by that theorem. And it is. You can check that it doesn't have any roots, and checking roots is all you need for quadratics and cubics. So that comes as close to failing as you can because it's barely eked by. Why is it true in general? Well, proof. Suppose that the order of f is p to k. Then f is splitting field. Of x to the p to the k minus x. Right? Now, consider splitting field of x to the p to k n minus x. Now notice that this is a field of p to the k n elements. So the dimension of a vector space of this over this, let's call the splitting field something, E. The degree of E over F, dimension as a vector space, is, see that's P to the K, P is N. And E is algebraic over F. And not only that, E equals F alpha, where alpha is generator of the cyclic group E star, right? Because this field right here is a finite field, so its multiplicative group is cyclic. It's generated by a single element. We know, in fact, we pointed out earlier that any finite field is a simple extension, and in this case, yeah, actually, it's a simple extension of CP, and so it's a simple extension of this. Therefore, alpha is of degree n over f. So f must have an irreducible polynomial of degree n. Whatever the minimal polynomial of alpha is, has to be its minimal polynomial, and whatever that polynomial of degree n is, it's a divisor of this polynomial. So that irreducible polynomial, in fact, I'll go you one step further. Every single irreducible polynomial of degree n will be a factor of that, be one of the factors of that polynomial. Okay, I'm going to leave you with one final little tidbit about the Galois group. I've sort of hinted about this as we've gone along. Theorem 14.6.8. Let's say that K is a finite field and F is a finite extension of degree n. And degree of F over K is n. So it's just some finite extension of your finite field. Then F is finite in Galois over K. Finite and Galois over K. It must be because it's a splitting field of a separable polynomial. And the Galois group of f over k is 60. And it, of order n, of course. And it's generated by that automorphism we talked about earlier. Okay, I will see you folks hopefully on Monday.